Amid the excitement surrounding the Starship Flight 4 launch schedule over the past few days, another issue has garnered significant attention. The cause of the explosion of both the Super Heavy and Starship during the third Starship launch has just been updated in the latest SpaceX announcement. So, what went wrong with the vehicle in the third Starship launch? How did SpaceX solve this problem? And what does SpaceX use those solutions? Let's find out in today's episode of Alpha Tech. On May 24th, alongside announcing the official launch date for the fourth Starship flight, SpaceX released a detailed update on the third flight. The update seems very timely to answer all the mysteries we've been wondering about for the past 2 months. During the third flight of Starship, when the second stage of the rocket reached space, the vehicle was subsequently lost during its return journey. The vehicle began to lose altitude control during its movement in space. This loss of attitude control resulted in a non-nominal re-entry into Earth's atmosphere. SpaceX was able to maintain communication with the vehicle up to an altitude of 65 kilometers before telemetry was lost due to excessive heat. The most likely root cause of the unplanned roll was determined to be the clogging of the valves responsible for roll control. In response, SpaceX has added additional roll control thrusters on upcoming Starships to improve attitude control redundancy and upgraded the hardware for better resilience to blockage. This appears to be part of the reason why SpaceX did not attempt to restart the Raptor engines during the upper stage flight of Starship, indicating that these new roll control thrusters had not yet been implemented. Also, during the third flight, SpaceX attempted a soft landing of the Super Heavy booster, but was unsuccessful. After separating from the Starship's upper stage as planned, 13 out of the 33 Raptor engines on Super Heavy successfully reignited to execute a controlled flight through the lower atmosphere. However, during this boostback burn, 6 of these engines shut down early. During the landing phase, as the rocket approached the sea, it was supposed to use the same 13 engines for the final landing burn. The 6 engines that shut down early in the boost back burn were disabled from attempting the landing burn startup, leaving 7 engines commanded to start with 2 successfully reaching main stage ignition, the company said in its recap of the flight. The booster had lower than expected landing burn thrust when contact was lost at approximately 462 meters in altitude over the Gulf of Mexico and just under 7 minutes into the mission. SpaceX explained that the root cause was filter clogging in the liquid oxygen supply to the engines, leading to a loss of input pressure in the engine's oxygen pump turbines. SpaceX made hardware changes before Flight 3 to mitigate this issue, which allowed the booster to attempt its first landing burn. For Flight 4 and beyond, the Super Heavy booster will have additional hardware inside the oxygen tank to further improve propellant filtering. Using the data collected from Super Heavy's first landing burn attempt, additional hardware and software changes are being implemented to increase the reliability of the Raptor engine's startup during landing conditions. To understand more easily, SpaceX is using rocket propellants, fuel and oxidizer, that freeze at different temperatures. The tanks and pipes carrying these propellants are in contact with each other. As the propellants flow through the system during the flight, the changing temperatures and pressures can cause some of the propellants to partially freeze and form slush or ice flakes. These ice particles could then clog the filters in the system. SpaceX is working to redesign parts of the system and adjust operations to prevent this ice buildup issue. Surprisingly, the problem seems to be occurring more with the oxygen propellant rather than the methane fuel. For now, SpaceX appears to be focusing on making the rocket systems more tolerant to debris as a short-term solution, while they continue working on a permanent fix for the ice buildup problem. However, SpaceX's hardware refinements might cause the dry mass of the Super Heavy booster to increase continuously, which is a disadvantage for the booster's landing. Another possible reason could be that the fuel tank used for the booster's landing was originally designed for a lighter booster weight before they decided to keep the inner stage attached during the landing. Indeed, don't forget that the hot stage was only added after the first flight. Before that, SpaceX hadn't designed any intermediate components between the 2 rocket stages. So, how did SpaceX address this issue? Well, although this is my personal speculation, the explanation seems quite logical. SpaceX did something they hadn't done in the previous 3 flights, sacrificing the hot stage ring after it had completed the mission. This is also mentioned in their updated timeline for the 4th flight. At T+354, SpaceX will perform the process of getting rid of, or as they call it, jettisoning the ring. By doing this, SpaceX can reduce the booster's weight to better match the vehicle's tolerance. This helps ensure the booster has enough propellant to slow down and land properly. It'll be interesting to see if the company's engineers can successfully solve this issue. However, many believe this solution is part of SpaceX's iterative process. They'll likely do this temporarily to better understand the landing process. Once they do, the hot stage ring won't be discarded, as that would not align with their plans for full reusability and rapid turnaround. In addition to the change involving the removal of the hot stage ring, the launch timeline for SpaceX's fourth flight also has some notable differences compared to the third launch. In fact, a detailed timeline of the entire Starship launch process for Flight 4 has been posted in our video from May 25th. If you want to learn more, click on the video link pinned in the comments. Now, here are some of the differences. One of the notable pre-launch changes involves the fueling process. During Flight 3, SpaceX began by loading the Starship upper stage with liquid oxygen first at T-minus 53 minutes, followed by loading liquid methane on the ship 2 minutes later. Flight 4 flips that around and starts with liquid methane first at T-minus 49 minutes, and then liquid oxygen 2 minutes after that. Similarly, on the Super Heavy flight, Flight 3 started with liquid oxygen loading at T-minus 42 minutes, and then liquid methane a minute later. Flight 4 begins with liquid methane at T-minus 40 minutes and then liquid oxygen 3 minutes after that. SpaceX did not state a reason for the reversals in the fueling process, but they've been doing quite a bit of work to modify the storage tanks for both the liquid oxygen and liquid methane in the tank farm near the pad. The vertical tanks were replaced with horizontal ones over the past several months as part of the work on the ground systems. All told, the timing for fueling Starship is set to be about 4 minutes shorter than the last flight. It's only about 11 minutes longer than it takes to fully fuel a Falcon 9 rocket. The launch timeline is also somewhat tweaked. While the end of the mission, pegged as an exciting landing, remains at roughly the same time in the ballpark of 1 hour and 5 minutes, Flight 4 streamlines much by removing some of the additional flight goals. 3 key events were added to the timeline, though, 1 near liftoff and 2 towards the end of the mission. Besides the mission to jettison the hot stage adapter to reduce the flight mass that I mentioned earlier, the other 2 events added in the next attempt include the so-called landing flip at T plus 1 hour, 5 minutes, and 38 seconds, followed by the landing burn 5 seconds later. The launch date is not far off, although SpaceX has publicly stated the latest launch date is June 5th. That still depends on receiving approval from the FAA. The SpaceX-led mishap investigation following Flight 3 remains ongoing, but the company's hoping to utilize a pre-existing clearance mechanism within the FAA's rules to return to flight before the investigation fully wraps up. During Flight 3, neither vehicle's automated flight safety system was triggered, and no debris impacted outside of predefined hazard areas, SpaceX said. Pending the FAA's finding of no public safety impact, a license modification for the next flight could be issued without formal closure of the mishap investigation. When reached for comment, the FAA confirmed receiving SpaceX's request for a public safety determination. Should they agree, SpaceX could indeed fly while the mishap investigation progresses. The FAA is responsible for and committed to protecting the public during commercial space transportation launch and re-entry operations, the agency stated. On April 5th, SpaceX requested the FAA make a public safety determination as part of the ongoing Starship OFT-3 mishap investigation. The FAA is reviewing the request and will be guided by data and safety at every step. Frequent and consistent launches are crucial for SpaceX's development process and for NASA as well. The rocket's contracted to support a crewed lunar landing during the Artemis 3 mission, currently scheduled for September 2026. A nearly year-long delay from its previous December 2025 target date as announced by NASA earlier this year. And that's all for today's episode. Thank you so much for watching and see you next time.